Hi everyone, thanks for coming. We'll start today in the Apache Flink Bay Area Meetup group. We have two talks, one from Gyula Fora from Cloudera and one from Lakshmi from Lyft. And thanks for coming. We are really excited to host you here in Cloudera. And I'm Marton, and I would like to start with giving you a little outline of how Cloudera is investing into Flink and why we are really excited to welcome you here today. So what we are seeing overall within our customer base is data in motion as a reference pattern is getting more and more important. People would like to be able to extract business value out of live updates. And let's consider the following use case as a general blueprint of dealing with streaming live data set. Let's say we have trucks out in the field, and we would like to be able to give them live updates on dangerous situations or track them on a dashboard and so on. In this case, we offer tooling in Minify to actually track the trucks themselves, as in an IoT pipeline where you can dynamically reconfigure these and then push the updates to Kafka. We offer data collections tooling via NiFi, and then processing capabilities where we primarily promote Flink. So that would be the reference idea of a proper platform when it comes to data collection, data storage of streaming data, and then data processing via Flink. And in terms of what Cloudera is trying to contribute to Flink, I would like to show you a couple of ideas on what Cloudera has been doing for NiFi and Kafka. And the general theme is the enterprise platform. Of course, this means all the usual governance, provisioning, configuration management bits, but it also means operations. So for example, on the right-hand side of the slide, you see the Streams Messaging Manager UI, which is an operations/monitoring tool for Kafka that Cloudera has recently contributed, where you can properly drill down into a Kafka topic and understand the consumers, the producers, the end-to-end latency, and so on. So that's roughly the expectation that you can have when it comes to making this an end-to-end platform. And that's the mindset that we have in terms of our commitment to the Flink community. So of course we start with the let's say necessary platform integration. We do focus on security, like adding support to Ranger, Atlas, and Nox. We are working on new connectors. So out of these, we have already implemented the Cloudera schema registry. We have implemented a streaming connector for HBase, and we are contributing these back to upstream Apache Flink. Kudu is next on that list. And of course, being there for the community. So we have given a keynote and 2 talks at Flink Forward. We are actively organizing some of the meetups just as this one. We are working on blog posts, so we would like to be there for you in terms of content as well, and giving you ideas of and blueprints of how you should be using Flink, in our opinion. In terms of our current status, Cloudera has invested into a Flink team. They hired 2 PMC members. You will see 2 of those on the stage today. In terms of partnership, we are looking into folks who are already invested into Flink and trying to come up with joint offerings. We have a private beta program. Actually, it's going to go live tomorrow. I was hoping to get it done by today, but of course, it had to be delayed just a slight bit more, but tomorrow it will be live on the website. And in terms of GA, we are looking at a Flink release on Cloudera in January. So with that, I'm passing the mic to Gyula, who is going to talk about log aggregation in Flink.
So welcome everyone. Thanks for joining us. My name is Gyula, and I work together with Marton in the Flink engineering team at Cloudera. Today, I'm going to talk about a very boring topic, but everybody has to deal with this at one point in time. So the talk is about log aggregation for Flink jobs. So let's start with the base definition of log aggregation for those of you who are unsure. So log aggregation is the process of collecting the logs from different sources, organizing them in a way that gives you a holistic view of the system so that when something goes wrong in a distributed application, you get a chance of debugging it. If you've used logging before, you know that it's a crucial part of application development. If you forgot this, you probably had some sleepless nights for your production applications, or if it wasn't configured correctly, when you get into trouble when something actually breaks. Yeah. So log aggregation usually has a few basic components that every logging framework builds on. So the first component is, of course, log collection. How do I get the logs from my applications? This is usually in the form of a log appender or something like that. The second is usually the log ingestion component that takes your logs that you've collected and puts it into the logging framework in some storage layer. The third component is the storage itself. It usually comes in the form of a search engine, because just looking at the logs and like browsing through them is usually not enough. When you want to debug your application, you actually want to search in the logs what went wrong. And of course, the last component, which is very helpful for production applications, is some sort of a logging dashboard. So you can quickly glance at the dashboard, see that it's going well. Do you get some errors in your log and stuff like that? So what are the requirements from the logging framework for streaming applications? So log aggregation itself is applicable for any distributed applications, but stream processing applications pose a few extra requirements. So first of all, we need very low latency access to the application logs. Collecting the logs afterwards, like systems like Yarn do, is not always good enough because you want to get the logs in real time. Also, you need scalability, both in terms of log collection and ingestion and storage. These streaming applications run over a period of weeks, months, even years. So the aggregated amount of logs can grow quite substantial. Also, you want to have some nice real-time monitoring capabilities for these logs that you can implement to get some alerts when something goes wrong. And of course, the logging framework itself should be easy to operate, but this is a standard requirement. So in this talk, I would like to show you how you can build log aggregation from scratch for Flink jobs using Flink itself and some standard components that might come from the Cloudera stack if you're using Cloudera. But these are generic open source tools that you can use to build your own logging framework if you don't already use one of the off-the-shelf solutions. So the way you can build a simple logging framework on the Cloudera stack would be to implement log collection using Kafka. So your logs would be collected into a Kafka topic. You could implement log ingestion itself using Flink streaming. It's a great fit for this because it provides you the low latency ingestion that you would need to quickly get your logs to your logging framework. Logs can be stored in Solr, which is the search engine included in the Cloudera platform, and you have Hue as a dashboarding tool to quickly visualize your logs. So let's start with the log collection. why do you want to choose Kafka for that? So Kafka itself has a lot of nice features that make it a great log collection / storage layer. It is very scalable, and it's very easy to talk to. So you can just configure a log appender that will push the logs to a Kafka topic, and then you can implement log ingestion on top of that. So how do we configure our Flink jobs to log to Kafka? Well, we're lucky because Kafka itself comes with a nice log4j appender. So we can simply use this in our log4j configuration. We can configure the Kafka topic where the logs will be written. And also we need to configure the Kafka broker properties. And of course, if you're running in a secure environment, there's a list of other settings that you have to set, but those are not very interesting right now. The other question that comes up once you decided that you're pushing logs to Kafka, the question of the event format. So by default, when we're looking at logs, we're usually looking at like a tab delimited format or a space delimited format, something that is easy to read. But this is not exactly the format that you want to push data, to push Kafka, because it's going to be very hard to ingest afterwards. You're going to have to write some parser that will parse this space delimited data. It's going to be a nightmare. So we decided to promote JSON format, and Logstash is an open source JSON formatter that we can use. So you can easily configure the layout for the Kafka appender to use the JSON format. One other thing that you don't get out of the box when logging in Flink is information about the task manager which logged your messages. When you log something, you usually get the host name, but if you're running in a containerized environment where multiple task managers run on a single host, you will want to be able to separate the different Flink applications and Flink task managers from each other. So in case of Yarn, the most straightforward way of separating these would be attaching the container ID to the logs. Oops. Yes, I need some help here. Yeah, so at the end, if you don't mind. If it's super important, then you can ask it in the middle, but otherwise at the end. Yeah, so we would like to attach the container ID. Unfortunately, this is not something that comes out of the box, and in general, it's not trivial to do with the logging framework. Unfortunately, there are certain things with SL4J that makes this pretty problematic in general. But one thing that we can do is configure the layout itself so that it includes an extra field in the JSON from the environment of the Flink application. So log4j1 is not smart enough to understand environment variables. It only understands Java properties. So there you can see the $yarn container ID would not be resolved if it was an environment variable of the Flink container. So we have to set it as a Java property. We can do this by configuring our Flink environment parameters so that we include the Yarn container ID Java property based on the container ID environment property. So this is a bit hacky way that will give us what we need. But now that we configure this correctly, we should see messages like this in our Kafka topic. So in addition to the standard fields of the log, we will, in the middle, you can see the Yarn container ID field. So now we can use this information to group our application logs by Yarn application and also Flink task manager. So now that we have our logs in Kafka in a nice, easily parsable format, the next step would be to implement the log ingestion. We will do this with a simple Flink application. There are 4 steps that we need to do. First, read the JSON data from Kafka. This is a pretty typical use case for Flink, reading data from Kafka, doing some parsing on it. We will parse the JSONs into these maps. We will do some cleaning and transformation on this JSON. We will drop some fields that we don't care about. Then we will batch these log messages into small windows so that we don't overload the search engine when we try to index the messages. And then we will use the Solr Java client to simply index them. So we can look at some Flink code. I hope the font size is large enough so that you all can see it. So the first step, as I said, you read the log stream. There are some hidden details, but everybody can imagine the Kafka consumer-based code and some flat map to parse the logs. So the result is a map of the string parse JSON object. And then we can key by yarn container ID so that we preserve the order within one task manager. This might or might not be necessary based on the engine where you're ingesting the logs into. And then we apply a simple processing time windowing logic to batch the logs so that instead of indexing them one by one, we take all the logs that happen in the last 2 seconds and index them in one step. So then we apply this Solr indexer operator. Here's the gist of it. So it basically is gonna create some Solr documents based on these string maps. The whole Solr document concept maps directly to these JSONs with named fields. So we can just shove everything into Solr. And if we do that, we can just open the Hue dashboard and get a pretty nice dashboard out of the box. We can see the logs. So for all of you who have used another logging framework, this is pretty much the dashboard that you get in Graylog or in an ELK logging framework. All right, so now that we covered how to build it ourselves, we can, of course, look at how other people have built it before us. So I'm sure many of you are using some logging framework at your company. So we're gonna quickly go through 2 of the 2 widely used solutions that are out there. So first is, of course, the ELK stack. If we look at the components that build up this stack, we can map it directly to what we built ourselves. So we can still keep the Kafka-based logging approach, but here the log ingestion will be done by the Logstash component. Instead of Solr, we ingest our logs into Elastic, and the dashboarding layer will be Kibana. So the nice thing about logging to Kafka is that most of these logging framework actually support Kafka as a source. So if we have the Kafka configuration properly, then we can also ingest the same logs into Elastic using Logstash. So for Logstash, instead of having to write this Flink job that does this for us, Logstash is already running, so we just have to make sure that we configure it correctly, that it picks up the JSONs in the correct format. So we configure it to read from Kafka. We provide the host name for the Elasticsearch cluster, and we have to do some JSON mapping. This is what we would have done in our parsing logic in the Flink job. This is how you configure it for Logstash. I'm not going to go into the details here. If you're interested, you should Google it and you'll find out. The Kibana dashboard that you get at the end looks very similar to what you see in Hue. I mean, both Hue and Kibana are just these generic dashboarding solutions, but they're pretty much suitable for logging, and they give you a nice experience over the Flink UI, definitely. So let's look at another solution that is widely used at many companies. Graylog is a framework or system that is made specifically for log aggregation and dashboarding. So here we can still keep our logs in Kafka, so we don't have to change the logging configuration. But what's going to change is the whole ingestion and dashboarding side of things. So Graylog takes care of the ingestion itself. It also puts data into Elasticsearch, and it relies on MongoDB in the background for keeping some metadata. As for configuring the ingestion itself, out of these three systems, this one probably has the nicest user experience for configuring the Kafka-based logging. You can just click through the UI and set up the Kafka input for your logs, add some extractors that specifies that it's in a JSON format, and how do you map some of the logging fields to what Graylog expects from you. The resulting dashboard, again, looks pretty similar. There is not much to reinvent here. It's just the same. You can search the logs, and you can create nice dashboards and alerts similar to Kibana and Hue. All right. So to give you a quick recap of this presentation, so log aggregation is an essential part of every distributed processing application, especially if you are moving to production. Kafka provides a very simple way of collecting your logs, and we've seen that you can easily integrate it with any logging framework. Most logging frameworks are built using the same kind of components. It's not magic. You can build your own logging framework from scratch if you don't have any at your disposal in the company. And both custom and off-the-shelf solutions work great for Flink. It's much better than not having any. All right. Thank you very much. Okay. So please, any questions?
So the real power of Flink is actually doing analysis on the data. So have you looked at turning the log messages into events? And then, it's like when you lose a slot from a task manager, and that triggers another problem, and you're sitting there wandering through 30 log files trying to figure out what actually went wrong. It seems like that could be something that you could actually extract in the Flink workflow.
Yeah, I think this is one thing that you could do in your custom approach, where we index them in Solr. You could improve this job and add some capabilities to actually try to analyze your logs in real time. So not only could it ingest it into the search engine, but you could also do some complex event processing, for example, on the logs themselves, to try to build some more sophisticated alerting logic that might not be possible to do within the logging framework itself. Yeah.
I just don't quite understand what's your decision to using Kafka, for example. It seems to me that you go from Flink and you go to Kafka for collection, and then your log aggregation is another streaming kind of application again, which goes to Solr. Is that correct? So why not just get rid of Kafka in between? What is the design considerations there?
Yeah. So you're right in the sense that if you have a Flink application, you could kind of have a way to go to Solr directly. I mean, you could probably implement a log appender that would write to Solr directly, but that would mean that the log ingestion itself is decentralized and is executed in all the different applications. By writing to Kafka, you kind of centralize the log ingestion itself. And I think this is a much more scalable approach. You don't have a multitude of clients trying to connect to Solr at the same time. And also, this might put like a performance overhead on the logging itself.
So why not just create a merger then? Why don't you just merge the streams together then, if you're worried about overflowing Solr?
But could you please tell me, how would you, what do you mean by merging the logs? Because you're logging from different applications.
Right, just make hierarchical, right? So if you take 2 streams, why can't you just merge 2 streams and then merge 4 streams, merge 8 streams, etc.?
Yeah, I think this is exactly what happens when you start logging to Kafka, because you have many producers that write the messages. They all produce their own stream of logs, and basically by writing to Kafka, you merge them into a stream of Kafka messages. You merge them into a Kafka topic that you process at one time in your log ingester.
Right, I'm guessing why not just do it in Flink?
It's pretty much open. It's fair game. Everybody can, any application can come grab it. It also serves as a buffer to protect your downstream applications. Because if your downstream Flink, if a Flink choke or for any reason Flink is not available, Kafka, your data is still there. You do not have to, because your application may produce a log and then the log will not be lost. It's basically a protection, a buffer, and also to eliminate point-to-point solutions.
Yeah. Also, I don't know how would you even collect the logs of a given Flink application in the same application. So how would you do that? Would you how would the logging itself work? All right, maybe we can take this discussion offline so that we can elaborate more on the details, because I'm not, I don't think I fully understand your suggestion.
Quick question here.
Oh, sorry, I'm like looking at there.
Yeah,
sorry.
It's too close.
Trying to pretend that I know where you are.
So you said that streaming application, they have special need that they need like real-time access to the logs.
Yeah.
I have seen a lot of like cases, but I rarely like actually go to the real-time log and like try to see what is happening like in the last second. So do you mean do you mean you want to use this as an alerting or like as a developer, would you like look at the last second log or?
I mean, sometimes you want to look at the logs themselves, but you're right. If you're actually looking at them, it doesn't have to be real time. But if you want to build some sort of alerting mechanism on top of it, I mean, this can become crucial to get the latency as low as possible, because sometimes these applications operate like production critical or mission critical like business functions where every second counts.
Hi. Are you not using Logstash at all, or is it being used in some way?
Well, Logstash is used for log ingestion in the ELK stack. So I had the example where you would log to Kafka, you use Logstash as ingestion to Elastic, and you use Kibana for dashboard. So in that case, you would use Logstash, but it's just another way of ingesting your logs.
The reason I asked, if you're using ELK, you have to use Logstash.
That's how I.
And the one big problem we have with Logstash is with exception stack traces. It tends to divide it into multiple JSON documents, and then you have to kind of stitch it together.
Okay.
So do you have a similar problem with what you do with Flink?
Yeah, I mean, in this case, since we wrote the log ingestion step itself from scratch, we made sure that we don't split the log messages. So I think what you can do in that case is you just make sure that the Flink job that you've written will not do this. I'm not sure if you can configure Logstash like this. I don't have too much experience in digging into the details. but maybe somebody else can help with that. I don't know.
Excuse me, I have two questions. The first one, can you talk a little bit about deployment? I saw Hue, Flink, Kafka, and Flink twice, right? I'm wondering, are those all in the same cluster? Or is it one like Cloudera managed cluster, or can they be like on-prem and in cloud? And is there any distinctions around that?
Yeah. So in theory, there's no restrictions on where these different services have to live as long as they can talk to each other. Of course, in most cases, the Flink job will live pretty close to the Kafka cluster, so that the communication is nice and smooth. I mean, in the Cloudera platform, these are on the same cluster environments. So all these components. So the components that I mentioned here for the custom solution, those are all systems that are part of the Cloudera platform. So they live on your cluster.
Okay. Second question was about that yarn container ID. I saw that like key by yarn container ID, and then you were specifying the container ID when you ran the Flink job.
Yeah.
Could you go into more? Can you explain that again? Because I didn't get it.
Yeah. So the point of having the the main problem that we're trying to solve is that if you start a Flink application that starts to produce some logs, you don't really get contextual information about which operator or which task manager logs these logs. You get things like host name and class and whatnot, but if you run multiple instances of the same Flink application on the same physical host, these logs will be impossible to separate from each other because you don't have any context information that you can use to make the separation. So we used the yarn container ID to tag each log message with this extra information that can be used to identify the Flink application itself and also the task manager container. So we can separate both Flink applications and task manager containers from each other. Yeah. Did that answer your question?
It does. There could be other tags. So like you could have had something in your application that.
Yeah. I mean, so the question was that if you could add other tags, or we could use other tags to make this distinction. I mean, one other thing that you could do is before starting a Flink application, you hard code some extra tags like your own custom application identifier. This is something I've done in the past, and it's very nice. But the good thing about the container ID is that you can get it dynamically, so you don't have to change the logging configuration before you deploy the job. So it just works, and it will be different container ID for each task manager. All right. I think we still have some time because I mean we are in control here. So we're not going to take away from your time, so don't worry about that.
Question here. So have you thought about exposing those logs through like a SQL table that you can from Flink itself? Let's say I do like a select and I group by some of my custom fields and I do like some special, let's say, SQL statement. So have you thought about exposing it in a SQL table and that avoids all the cabana, whatever you name it in the end?
Yeah, I think once you have your logs in Kafka, it provides a very simple interface for your Flink jobs to consume them and implement any application on top of it. I think it should be fairly straightforward to implement a table source that will map these parsed JSON objects into like a Flink like rows, and then you have a table that you can write some queries against. So I think that the solution is the Kafka logging itself, and Flink already provides the necessary interfaces to read from Kafka. So
In your deployment, what type of processing guarantee it offers?
Yeah. Well, in this case, we didn't really add any strict processing guarantee for the logs, so we were just running with without any checkpointing in our prototype. It's usually, I mean, ideally you would have proper exactly once guarantees for your logs so that log analysis becomes very straightforward. Yeah, so I think if you want to build this in production, you will have to make sure that you don't lose your logs, or if something breaks in your log ingester, you can like react to it and fix it. Well, this is just a homemade implementation. I mean, it definitely supports at least once processing, so yeah, we can't guarantee exactly once logging to Solr. So if the Flink job fails and we have to reprocess it, we're not, yeah. Yeah, so I don't have a general answer to that, but I guess any container framework or any deploy environment that you're using should have some concept of a resource identifier that it exposes. So you have to check what you can access from the environment. Maybe you can do the same trick. I mean, most likely it's going to be accessible as an environment variable for your Java program. If not, maybe you can make a small modification to include it in Flink. Yeah. Yeah. So this application assumed nothing about the structure of the logs. So it treated the logs themselves as just a map of strings that would be pushed to the search engine. So if the structure of the log changes, it would just be indexed. Yeah, I mean, you might, if you implement some custom logic, you might have to adjust it. Yeah, I think we should wrap up with the questions so we can continue with the second presentation.
Yeah, let's take a 15-minute break before the pizza gets cold, and then we'll continue with Lakshmi's talk.
Right. Thank you very much.
Thank you. So let's continue with Lakshmi's experience on running Flink in production at Lyft.
Hi, everyone. I'm Lakshmi. I'm a software engineer at Lyft on the streaming platform team. And today I'm going to talk about running Flink in production. So we've been running Flink in production at Lyft for almost 2 years now. Our first production job was deployed sometime in late 2017 or early 2018. And we've learned quite a few things along the way, and sometimes the hard way. So hopefully this talk helps other folks who are building platforms for Flink jobs. So I'm guessing everyone here has used Lyft at least once. Our main objective, as you know, is to match riders with drivers. And behind the scenes, that means a lot of things to make sure that your core experience remains pleasurable. For example, we have to constantly keep updating our demand and supply data to make sure that we price your rides fairly. And we also have to ensure that any kind of user experience, like notifications, calculating the ETAs for your driver or your ride, remains correct and accurate, and on time, it reaches the users on time. And apart from that, there's also fraud tracking and detection that we need to do. And all of this relies on data, and more specifically on real-time data. And so when we started investing in a streaming platform, Flink sort of naturally fit into that place because we wanted high durability, low latency, high throughput. I'll briefly go over what the data platform stack at Lyft looks like. So you can see that we have our mobile app and backend services. All of these emit events. An event can be anything that happened. It could be that a ride was requested or a machine learning model was executed by the pricing platform. So all of these events flow into our streaming sources or our pub subsystems. We have Kinesis and Kafka at Lyft. And from there on, we have users who want to consume these events directly off of the sources to do some kind of event-driven business logic in their applications. Or there are users who want this data to be transported to some kind of sink, like S3, which is a data warehouse, or any kind of database, DynamoDB, anything else, Elasticsearch. So since we have like sort of a diversity in the kind of users that we have at Lyft, it becomes quite important to understand what our users really need. At one end of that data pipeline spectrum are the analytics users, data engineers, and research scientists who primarily want to consume data from the data warehouse. And then somewhere in the middle, we have our machine learning engineers who build their own platforms, run machine learning models, but want to leverage Flink because it can do really well with heavy data processing and computation. And finally, we have backend engineers who want to write Flink jobs, manage Flink jobs, and who are comfortable operating it, and they want the control over it. So along the way, we have built quite a few abstractions to cater to the needs of these different users. And at the bottommost layer is our naive Flink jobs that are written in Java. All kinds of engineers write these jobs. They primarily use it for writing data pipelines, like the log ingestion data pipeline that Gyula talked about, and then building pipelines for ETA prediction and for like transporting locations data from a source to sink. And about 45% of our jobs are written in Java. And then the machine learning engineers who already have all of their services and platforms written in Python, simply because Python has a very rich machine learning support, want to continue to use that code, but want to use Flink. So we allow them to use Flink on Python via Apache Beam. And finally, the most lightweight abstraction is our streaming SQL abstraction. We expose this via a platform called Dryft. Lyft, Dryft, you get it right. So the primary users there are research scientists and data engineers. They just want to be able to describe the aggregation that they want to do with a SQL, and they don't want any of the managing of the job, any operational overhead on top of all of this. So they kind of want that managed service experience. And more than half of our Flink jobs are written in this using Dryft. And underlying all of this is the streaming platform. I'll talk a little bit more about what that actually does. And today my talk will mostly focus on the streaming platform layer and how to write simple Flink jobs in Java. Everything is pretty much built on top of the streaming platform layer. So how does a Flink job at Lyft come into being? Say you're an engineer who has decided to use Flink. We give you a boilerplate, which is essentially using an open source templating tool called Yeoman, where you can go and say, hey, yo, build me a streaming service called Hello World. And that sort of fills up your code with an example. We used to use the very famous word count example before, but then we realized that our users had a very tough time moving from that word count example to a production use case. So we modified that to be a bit more representative. So we actually have an example that reads from a Kinesis stream, does some aggregations and outputs data to a sink. And Kinesis is our primary pub/sub source, which is pretty much the major Flink source connector that we use. And when you're ready to, once the user is ready with the code, they package that into a Flink jar, which essentially uses consists of the application jar, a library layer, and the Flink distribution. The library layer has tooling to integrate with all of Lyft's internal stack. So it has metrics, logging to report stats to Wavefront, logging to send the application logs to Kibana, and also serialization and deserialization utils. And once all of this local testing is done, the user goes to Jenkins to deploy their Flink job. And the deploy creates a job manager and task manager like a Flink cluster. All of these are AWS EC2 instances. And we use S3 as our persistent Flink state, or for persisting Flink state checkpoint store. And once the job is up, once the cluster is created, the user uses a command line tooling to submit, update, and do any kind of interactions with the cluster. And once the job is up and running, we direct alerts using PagerDuty and Grafana, and logs are available on Kibana. So some early learnings from the whole development and deploy process has been that templates and boilerplate generators are very useful. They help users kickstart their jobs. But they also require constant maintenance. Like every time users need to use a new source or new sink, it kind of becomes hard to keep up with that. And automating observability is useful for our users because many of them are using Flink for the very first time. And populating logs and dashboards automatically helps them diagnose issues with their Flink job. And that leads us to basically user education is still a challenge because, as I said, Flink is still a first-time use for many of our customers. And it's pretty hard. We try to abstract away many of the internals, but it's still very sometimes challenging for users to understand the internals of Flink. And the command line tooling is an easy way for users to interact with the Flink cluster and their Flink jobs, but it's manual and hence very error prone. And once the user has deployed their jobs to production, hopefully they don't end up in this state. But we've had quite a few production stories, and I'll highlight a couple of them in this talk. Our connector ecosystem is pretty rich. We have Kinesis, Kafka, S3, Elasticsearch, Firehose, and we also have change data logs flowing from MongoDB and DynamoDB. But the connector that we have battle tested the most in production is our Kinesis connector. Right from the very first job that we deployed to production and up until today, we continue to use this. And today I'll talk about a specific problem that we uncovered and fixed with the Kinesis connector. So let's imagine that you have a Flink job that's reading from a Kinesis stream, and the stream has 2 shards. And you also, basically the job's responsibility is to read from the stream and do some windowing downstream. You have an event time scale that runs from time 0 to 100, and you're doing windows in 5-second or 5 time unit intervals. How the Kinesis connector works in Flink is it has a Flink source thread, and that spawns off shard consumer threads, 1 shard consumer thread per shard that is being read. And let's assume that for some reason, maybe a backfill is going on or some other thing to that effect is happening. And one of the shards has data that's sort of older or more behind in event time. And there's another shard that has more recent data that's, or fresher data in terms of event time. And you have the 2 shard consumer threads reading from that, and windowing the data. And when they window the data, now you can see since there's significant skew in the event time, you have windows in the first time t to 1 to 5. You have windowing in the second window, and you have data in the third window as well. Well, you might say, what's the challenge really here? The important thing to note is that all of this data is kind of windowed in state. Or it's stored in state until it can be actually used. And as this queue increases across the shards, and as the number of shards increases, say, instead of 2 shards, you're reading from hundreds of shards, and this queue is significantly higher as you, between all of the shards. Now you end up with a lot of windows in your state, and your state size keeps increasing. And when your state size starts increasing, it leads to inadvertent problems like your checkpointing times start increasing, and then checkpoints start failing, and your app soon is spending all of its time doing checkpointing and not making forward progress. And that puts it in a more backlogged state, and this vicious cycle continues. So what is really the way to fix this? So if you can see here, now we are reading data from the Kinesis shards, putting it and storing it in our state, and also storing the data in the Kinesis shard when it cannot be used. So essentially, we have 2 copies of our data somewhere when none of that data can actually be used. So the solution that is what we call source synchronization. And the idea behind that is basically to read only the data that can be emitted and consumed at a given point in time. And we do this by sharing state across all of the shard threads or the subtasks that are reading from the shards. So assume that now you have the same kind of dynamic. You have 2 shards. The shard threads are reading from these 2 shards. And now you introduce a queue or a buffer in between where the data resides there. And the source thread or the Flink source thread essentially decides which data needs to be emitted. And it does this by comparing it against a global watermark. You can think of the watermark as like the minimum event timestamp at some given point in time. And the Flink source thread picks data from that queue, compares it against the global watermark. If it's within a time range of that, it emits the data. Otherwise, it does not do anything with it until the watermark changes, or if older data ends up in the queues. So in this way, the data that actually gets emitted is more closer in event time, and the skew is reduced, and hence what you store in your windowed state is much lesser. And we did some experiments with this in production, and we found that, especially if you look at the second graph there, the checkpoint size that on the right was what it was when we didn't have this source synchronization turned on. And what you see on the left is what the size when we synchronized across all of our shards. And you see that that's much smaller than the other. This is one of the primary contributions that have been made, that we made to the Flink Kinesis connector. We've also done a few other contributions. The shard balancing one is essentially to ensure that shards are equally distributed across the Flink subtasks. And the adaptive reads is to make sure that we maximize the throughput of reads from the Kinesis stream. The second theme of production stories is around checkpointing. We use S3 as our persistent checkpoint store. And as a platform team, one of the things that we try to keep track of is why our users' jobs fail or restart. While one restart for one application may be an okay thing, if we notice any patterns across job restarts and job failures, we try to fix something at a platform level if we can. So one of the issues that we noticed was several applications would run into these transient errors in reading and writing checkpoints to S3. And this would result in frequent restarts, which was kind of expensive for these applications. So the solution was fairly straightforward. It was that we built a file system wrapper on top of the application layer, where we could control things like retries, backoffs, and customize our behavior whenever a specific exception happened from S3. And we extended that to the Kinesis connector as well and other connectors, where we control different types of different types of exceptions with different number of retries and kinds of retries. And all of this gets packaged into the library layer that I was talking about in the application image. And a second kind of issue that we ran into was purely because of the way S3 works. So our checkpoint path used to look like that, which is essentially a bucket, an application, and checkpoints, application name and checkpoints. This path was actually pretty bad for S3 because it resulted in hot partitions, which would mean that we'd get throttled by S3 when we were writing or reading from that path. So the fix for this was essentially using the entropy injection feature, which got introduced in Flink, that allowed us to introduce a hash in this S3 path, so that the data was actually written to different partitions in S3 behind the scenes. And a general recommendation is that you use that hash as early in that prefix as possible, as opposed to towards the end of that prefix. And finally, I think what we have benefited from is enabling externalized checkpoints for all of our user applications, because sometimes jobs end up in a failing state and you can't save point the job, and recovering job from state becomes hard. That said, we have fixed a bunch of things, but some things are still hard. One of the things is the fact that we have a lot of data pipeline use cases. For example, our log ingestion pipeline runs on Flink. We ingest logs into Elasticsearch using a Flink job. And a common requirement for these pipelines is that when they go down and recover, they want to start consuming real-time data, and at the same time have a way to backfill the data for the period of outage. And this is something that many of our users have sort of built some hacky solutions around, but we haven't really tried to fix this as a platform. And some other problems that I highlighted was checkpointing under back pressure continues to be a bit of a challenge, and ends up in this vicious cycle. And finally, we'd like to contribute all of that changes that we made for source synchronization in the Kinesis connector to the Kafka consumer as well. And some learnings here have been that bandwidth control is important. Any kind of throughput issues, especially when you run at scale, it's important to read the right amount of data. And it's important to also focus on making users' lives simple by building extensions on top of whatever connectors and external systems that we use. And we've also tried to invest in a performance workbench for every new connector that our users use to battle test it and run it at scale and identify loopholes before users identify them. And it's been pretty amazing to build a platform on top of an open source project. So what's next? Somewhere last year, I think we'd been running this pretty somewhat successfully for about a year, and then we started thinking about how do we address some of the shortcomings here and re-architect this so that we get some benefits from Kubernetes. So we started the effort of building Flink on Kubernetes. The key motivation being that in our old system with AWS and EC2 resources, deploying new jobs meant provisioning a whole world of AWS resources, which could take time. And every time you lost like a node without a spare, it would take 10 minutes for a new one to come up. And the command line tooling that we had, it was fine, but it was manual and error prone. And we also, any kind of common failure in the Flink job required a user to intervene. And finally, we were not running anything in a containerized way, so there was a need for immutable infrastructure. So as we started this effort, the core component that we built was the Flink Kubernetes operator. For those of you who are not very familiar with Kubernetes operators, you can think of it as a watcher, something that just watches your Flink applications all the time. And with this Kubernetes deployment, our workflow becomes a little simpler. The user specifies a job definition, and that's pretty much all that the user interacts with. The operator picks up the job definition and decides what to do with it and executes accordingly. It might be creating a new cluster, updating a running job, etc. And it'll become a bit clearer as I show you the state machine. So this is how the Flink application job definition looks like. It's called a custom resource definition. Custom resource because it's a custom resource and not a native Kubernetes resource like a pod or a deployment. So if you see here, we are trying to run a word count Flink app with a parallelism of 30 and with some job manager and task manager specifications. And the operator is responsible for bringing your Flink app to whatever desired state that the CRD specifies. And it's designed with this goal that any operation that brings down your app should either succeed, or if there's an error in that process, it should roll back immediately. For example, if you were to either create a new Flink job, or if you were trying to update an existing Flink job, the operator would first create a new Flink cluster, and then it would save point the job that's running on the old cluster, submit the job with the save point on the new cluster, and if everything works out fine and the job starts running, the operator goes back to just watching the job, waiting for other updates to happen. But if something messed up in this whole process, the operator rolls back the job to the previously running version and then notifies the user that, hey, your update failed, do something. And while the user investigates, most likely your job is still running and you don't really have any downtime. With this, the major wins that we have achieved is the improved stability. And we now don't have downtime due to common failures, like because we have this one place where we can codify all of these things. For example, if your job failed on submission, the operator automatically rolls it back instead of you having to come and intervene and figure out that your job failed to submit successfully. And because we have this place to codify some heuristics and rules, our tooling becomes easier to develop and it's way more predictable. And finally, it gives us opportunities to build more flexible deployment strategies. For example, think of zero downtime deploys and blue-green deploys with Flink, or with the backfill use case that I was talking about, it gives us an ability to run ad hoc backfill jobs, which is much harder with the AWS EC2 framework. Finally, we open sourced this operator in May this year, and it's already in production use at Lyft. We have migrated quite a few jobs from the legacy land to the Kubernetes world. And we have a bunch of external contributors and contributions, and it's also available on the Flink packages website that was released recently. So if you're interested, go ahead and check it out and ask questions on GitHub. We also have a Slack channel that's linked. So that's it. That's all that I had.
Hey, Lakshmi. Hey. Thanks for the great talk. Yeah. Wow, there's a really bad echo. Your source synchronization is really cool. Mm-hmm. I have two questions. One is, how do you handle the case when your source actually just has a gap, right? Like imagine your upstream source is maybe another Flink job or something like that, and it goes down for a while, and so your global watermark never moves forward. And the second question is, have you ever thought about using it for two streams? So we have this problem where we do a lot of like large-scale two-stream joins, and it's so hard when one of them gets behind or when we have a failure or something like that, because now they're at a different place. And so I could imagine that being another use case for it.
Yeah, so for the first question, when there's no data with the Kinesis connector, we actually have an idle shard detection that we do, and we progress the watermark if the shard has been idle for a while. And that's something that we contributed to the Kinesis connector, which I don't believe exists in the Kafka consumer yet. And the second case was running it across two streams, right? Yeah, I guess that should basically work. We don't have, currently what we have done is across just what we have tested is across one stream. We haven't extended it across multiple sources yet, but Thomas might have a better answer for that. Thomas?
Yes, so you could use it with multiple sources too. It could be in a test. We also have done a file source and a stream, Kinesis stream. The thing is, the shared information is in one place, a global watermark that could be fed from two different connectors, different sets of subtasks, and they would synchronize each other. So for example, what you could do, read from two Kinesis streams, configure them with the same global watermark sync, and then they would advance accordingly. Or you could have a file reader and a Kinesis consumer and configure them with a single shared global watermark, and they would wait for each other as necessary.
Yeah, our primary use case for this is like the bootstrapping that we do across S3 and Kinesis.
Hi. The source synchronization, can you specify which version of Flink it is available in?
I think it's Flink 1.8.
Okay.
Yeah.
And the second question was, since you are starting a cluster per job, is it still a EMR cluster in AWS, or are you using EC2 instances and you're installing Flink as well on that?
Yeah, so in the non-Kubernetes world, it's EC2 instances. And we have a bunch of deployment stuff that pulls in the Flink distributions and starts up the task manager and job manager processes. So we don't use EMR.
So also two questions. So the first one is, have you tried using the watermarking to deal with the cold start problem, like where you're reading from batch and then, to kickstart stuff, and then you start reading from a stream?
Yes, we haven't, that was kind of the aim of building all of this work, because we have, like I mentioned, the Dryft platform that is a streaming SQL platform. Often we have jobs that have loopbacks of like a month or something like that, and all of that data is not available on your Kinesis stream. So we read from S3 and we read from Kinesis, and the objective of source sync is to actually be able to synchronize across those sources, but we haven't gotten around to testing it with that streaming SQL platform yet.
The second question is, so you've got a lot of patches. What's been your experience getting those actually rolled into Flink?
I'd say we've had a pretty positive experience doing that, especially with my experience has been mostly in the Kinesis connector work. And I think one thing that's been beneficial is that we've been able to test we have an internal fork where we sometimes test some of our patches at scale with some of the jobs we have, but we always try to contribute those patches back to Flink like pretty much immediately. So we've had a good experience doing that.
Question. So I was just wondering, can you speak a little bit about your job partitioning, meaning that Dryft is kind of like a SQL kind of analytic stuff, and Flink is doing some part of the job. So can you tell a bit about what jobs get to be put where?
Like, do you mean how people choose between Dryft and?
Correct, and yes.
Yeah, so I think it essentially comes down to the use case and the user. Most of our machine learning feature generation jobs in some of the teams, they are run by research scientists, and research scientists often don't have experience operating or running streaming jobs at scale. So they prefer to describe their jobs in a SQL and then have like someone who's experienced at running streaming jobs manage that for them. So typically research scientists are the ones who fall into that streaming SQL category. And most of the Java Flink jobs are written by data engineers or other software engineers within the data team because they're typically well-versed with big data stack in general. So they're comfortable managing their own jobs.
Cool.
Yeah.
I have a second question about the file system wrapper that you wrote. And you said primarily that's happening because you have a lot of transient errors during reading and writing, right?
Yeah.
During checkpoints. Why are there so many errors happening?
I mean, well, S3 is an external system that it's not necessarily eventual consistency, but sometimes it has internal errors, and it's really hard to tell why S3 errors at times. Okay. One of them was also the throttling errors that we saw. So that was solved by the other hot partition issue, fix the entropy injection feature. But that's the nature of those errors. They're transient, right? Like it's very hard to go and diagnose exactly what happened, what S3 was facing at that point in time.
So for your entropy per injection, what are you hashing on? What's the key that you're hashing on?
We don't. So we essentially, I think you can specify like the number of characters you want in your hash. So it's essentially a random hash. So it's a random 4-character string. So it's not keyed by anything.
It's a random one. Then you have a lookup table for those then.
Yeah. So I see. So the checkpoints have the actual checkpoint data, and they have a metadata file which tells you where your checkpoints are, and the metadata path is not hashed. So that's deterministic.
Hi.
Hi.
Hi. Thanks for the sharing. Can you elaborate more about the page 19 about the diagrams, the synchronization part?
Yeah. Yeah, sure. Do you want to just know about it more? So I guess, okay, I can talk a little bit about each of those graphs. So, so the skew that you see at the top is essentially the skew that's downstream of the records being emitted. So when there was no synchronization being applied, all the timestamps across all of these records was significantly different from each other. One was really far ahead, one was really far behind. So the skew was, you can see that the skew is pretty large. And when the synchronization was actually applied, the records that were being emitted were tighter in their event time timestamp field. So they were, so you see that the skew is pretty small. And the second is kind of the effect of the first skew that you see. All of that skew, that means that you're having more data to store in your state because you're reading a lot of data that cannot be used immediately. And since you're storing a lot of data in your checkpoint size is really large in the second graph without the synchronization. And once the synchronization is actually applied, it becomes much lesser. Does that help?
How about the third one?
So the third one is essentially the same as so it's essentially the same graph, but it shows the iterator age, or that's the term for lag in kinesis streams. So essentially it shows that in the first graph, because there's skew, you can see that different kinesis shards have different kinds of iterator age that go down, whereas when the source synchronization is actually applied, there's a tighter band because all of them are read at the same rate.
Seems like one is at 9 a.m. and the other one is at 11 p.m. Isn't that like a different workload altogether?
No, it's the same Flink job. I mean, it's the same job that's run with that source synchronization enabled, and with the right side is without it being enabled. So with the source synchronization, you should see smaller state sizes, lesser skew in your data, and it's basically the same load. I mean, do you mean that due to the time of the day?
I mean, it seems like you have a peak at 9 a.m. That's with people that come at their work, and then
I think it's a backlog stream, right? Yeah, so it's a 24-hour or whatever. It's like reading from the beginning of the stream. Yeah.
It's the same job.
Yeah. Is disabled. It's 2 runs of that job. Yeah. So it's not the same job that's continuously running. It's essentially, we turned on the synchronization to do an experiment on the left-hand side between 8 p.m. and 11 p.m. at night. And we read from the beginning of the stream. And then we stopped doing that experiment. And the next morning at 6 a.m., we turned on another experiment without that solution being enabled and read from the beginning of the stream again, of the same stream again. So it's not meant to be a continuous job running. Yeah.
In the Kinesis shard late event scenario, were you buffering the data in the source connector?
Buffering the data in the source connector? Can you?
So my understanding was like you were buffering the data, but you're not emitting to the downstream. Basically, you're looking at the global timestamp, the watermark, and the timestamps from all the stream data, and then emit only the lowest watermark.
Yeah, so we have a priority queue in the source connector. Is that right? Is that how the?
So, like Lakshmi showed earlier, each shard has a separate consumer thread. Each of these consumer threads, they push the data into a queue. The queue per shard, per thread, will block when it's filled up. And there is the source thread that takes elements of the queue. It will prioritize the queue with the lowest timestamp, and it will also only read until it reaches the global watermark plus a configured look-ahead time difference. If it reaches that, then it will stop reading from any of the queues and wait for other subtasks that may run in different machines to advance and move ahead the global watermark. So these queues provide a blocking function, and the source thread prioritizes which consumer thread is now able to emit. The purpose of this is to basically control the speed of the threads and the backlog, and keep the backlog out of the Flink application. So if data is not ready to be processed, we don't want to read it into Flink. We want to leave it where it is in Kinesis in this case, and only read it when we are ready to do so. So there is no, yes, there could be a backlog for a given shard thread, I guess, because the buffer is now filled up because the data is not ready to be consumed. But other than that, the purpose of the feature is to not create a state, large state inside the application with data that is not ready to be processed, but nevertheless has to be buffered up in Flink because we have already consumed it. We don't want to consume it. We want to avoid that memory consumption in Flink and that checkpointing overhead. Does it make sense? This is not a sorting feature here. The purpose of the feature is to prioritize reading from the original or from the set of shards, right? So this is approximately sorted, but yeah, the point is not to sort records. We are just controlling the speed at which different shards are consumed.
Mm-hmm. Flink SQL or Kinesis? We don't use Kinesis SQL. So basically, we use Flink SQL. It gets converted into a streaming SQL job. But the users actually don't write a Flink SQL job. They only describe their SQL. The platform converts that into, parses that SQL, creates a stream. It's just a basic DSL parsing of that user config.
Okay. Let's take the last question from Jeff, and then we'll take the rest offline.
So I understand the source synchronization, like what it's doing. Mm-hmm. What I don't understand is why it was needed. Like Flink is supposed to be good at large state and managing large state. So I'm trying to understand what is it about your job that made the checkpoints really big or take too long and made the state really large? Like how is it different than a typical large state Flink job?
So our experience with large state has been that when you have, so what it basically leads to is that you end up in a back pressured scenario because now you have, like when you have large state, you essentially your sync time to actually write your checkpoint to S3, async time to write your checkpoint to S3 takes a long time. Even checkpointing the state locally takes a long time. And essentially, if you end up in this scenario where your checkpoint failures keep increasing, you basically just don't make any forward progress. And you also have this skew across your subtasks now, which might lead to your alignment times taking a long time as well.
Right.
So I guess it's a mix of skew versus with large state.
How long is a long time with the checkpointing? Like how long was it taking?
We've seen jobs that have that timeout on checkpoints. Like we typically have like a 10-minute checkpoint timeout.
Oh, wow. That's a long time.
Yeah. And we've seen jobs that timeout. I don't know. I mean, I don't really know the numbers on our largest state. Perhaps in the...
Those were hundreds of gigabytes.
Yeah.
Basically, there is no limit.
Yeah.
The amount of state that can build up there. I think what we didn't mention is there are various reasons why that skew can occur, right?
Yeah.
But let's say the skew does occur, and you can theoretically fill up your memory with state, and Flink can spend almost all of its resources just checkpointing instead of making forward progress with the application. At that point, we are stuck, and you're in a downward spiral with the entire application. That's what we observed.
Yeah.
But the reason is not any legit application behavior, but just that we are flooding Flink with state that it doesn't need. And the point here is to not read that data into Flink because it's better where it already is in the message queue. The reason why we find this queue, and it's not uncommon, especially with something like Kinesis, is there is in the hosted environment, there's different speed of consumption, different speed in the performance of shards, because on AWS side, these are also at the end of the day on different machines with different resources. So you will account this misalignment between different shards or partitions as the application is running. And it's especially observable when there's a replay of historic data, because we are reading as fast as we can. And now the difference in machine speed, for example, will become very noticeable, and it will lead to this state buildup. So we find that we don't want to spend time optimizing how fast Flink can write unreasonably large state. We want to keep that state out of the Flink application and have it work on the problem that it was intended for.
Yeah, I think Thomas put it well. Basically, it's state that, I mean, it has nothing to do with the application intending to write that much state. It's essentially state that should not build up. So, yeah.
Thank you, Lakshmi, for the gate.
Thank you. Thank you.